We'll proceed curl in calculus. Okay, so time has come that we will we will do the merging what we have been talking about, what we have had been talking about. Curl in calculus, but talking about the actual curl, we talked about the path independence. So, how path independence that works in calculus, how path independence that works in calculus, and then how it contributes as far as curling is concerned. So, how it contributes as far as curling is concerned. So, that is the question, and then this is how we will proceed. Okay, so we have talked about curling. We have talked about curling. If I have a vector, this is x-axis. Consider this is x-axis. This is x-axis, and okay, okay. Consider how I can say I should have one more. Anyways, consider consider this is x-axis. This is x-axis, and I want to calculate the line integral. We have talked a lot about line integral, vector field, force field, and so many things. So vector field is nothing but algebraic vector. A vector for which the components are algebraic equation, then it is called vector field. Otherwise, it is simple vector, static vector, numeric vector. If consider that if I have a vector that represent a force, then what is the work done by the force along a particular line? If that line is demonstrated, it represented by unit vector u. If I want to know the work done by a vector that is numeric vector, simple static vector 2i plus 3j, what is the work done by the numeric vector 2i plus 3j along a direction that is unit vector u from point A to point B? From point A to point B, then it is nothing but if that vector is V for victory, then V vector dot U vector, V vector dot U vector. It will come as a scalar. Dot product of two vector will come as a scalar multiplied by distance from point A to B. That is the work done. Work done from point A to B in direction of U vector, U unit vector, when the force vector V vector is numeric vector V dot U. If force vector is vector field, if force vector is vector field, if force vector is vector field, then it becomes, consider that is capital F. Vector field is represented as capital F. If it is capital F vector dot dr vector. If it comes to algebra, then calculus comes into the picture. Calculus comes into the picture because whatever entity, if it is algebra, then it has independent component. If it has independent component, then based upon the independent component, the algebraic equation will start changing. So vector field, if its components are algebra, then vector field start changing as per the independent variable is changing. So vector field is also called a function which gives lot of vectors, static vectors, if I keep changing the independent variable. If algebra comes into the picture, then every moment scenario would change. That's why it is calculus. Earlier it was v vector dot u unit vector. into distance, that was the work done. Now it is capital F vector dot unit vector u dr. If dr is nothing but a small distance, dr, not r vector, dr, the small distance. Why we are taking a small distance? Because distance, but if I take a line, small distance, if I take 2 points, point A and point B, point A and point B, if these two lines, if these 2 points, if these 2 points are connected by a semicircle, point A, point B are connected by a semicircle, then this is the line. If this is the line and if this is the force, then force into this displacement is the work done. But force is algebraic equation in the sense, if I calculate force at this point, then force is like this. If I calculate force at this point, then force is like this. If I calculate force at this point, then force is like this. Because if I see point to point, then x comma y coordinate is changing. Based upon the x comma y component, since force is algebraic vector, the vector direction and its power both are changing point to point. Not only that, we want work to be done from point A to point B. This line itself is changing. Can you see? It's not a straight line. I cannot say along x-axis or along y-axis. So force capital F dot u unit vector, along which I want the work done. Work done is force into displacement, dr or delta r. Capital F dot u vector delta r is the net work done. That is, at if I take any point at that point, what is the unit vector? If I take small strip here, that is delta r. If I take small strip delta r, this is big delta delta r. If I take a small delta r, that it tends to a straight line. This is approximation. Consider it. I don't like it, but consider it. If I take a very small part of this curve, which tends to be a straight line, then it will have a direction. It will behave like a vector which will have a direction. Consider that direction is unit vector u. Then force the, and at that point the vector field capital F. If I take that point, consider that point, the if I take a small distance, then still it has a beginning point and end point. Consider at any point or center of this portion the capital F, whatever it is. So capital F dot u vector, because direction of the strip. If I do this dot product, then I get the force vectors, force vector, the essence along the u vector. The force vector, how much? Like if I say this is a vector, then what is its effect along x-axis? F cos theta. What is effects of this vector along y-axis? F sin theta. What is effect of this vector along x-axis? F dot I vector. F cos theta or F vector dot I vector. What is this vector's effect along y-axis? Capital F vector dot j vector. J and I are unit vectors. So, like that, if I take as point A and point B, and there is a vector field capital F, what is the work done by this vector field from point A to B along the semicircular line? If that is the case, consider a small strip in the in this curve. It is so small that it will look like a straight line. If that is the case, then that small, what is the direction? Consider I take from here to here, then the straight line is like this, tangential at that moment. So this direction has a unit vector, right? Unit vector which has magnitude of 1, only it shows the direction. Consider that is u vector. Then force vector, because force is a algebraic vector, what is its value at any point inside the delta r section I have taken? If I take delta r section, what is the force in this delta r? So I can say capital F at delta r. capital F at any point in the delta R. So capital F, so all along I can say capital F dot U unit vector. U unit vector is the unit vector of that strip, single vector. Capital F dot U unit vector, that will give the F, the force vector field, its effect along the U unit vector. Capital F dot U unit vector delta R at the end. To find the actual work done, then I have to multiply by the delta R. Now, if it is very, now if I take in calculus term, because I have to do summation, so whatever I have got this force for this delta R, if I keep taking this delta R, delta R width from point A to point B, delta R, then there will be infinite delta R, because very small I have cut it down. There will be infinite delta R. If I take infinite delta R, then whatever work done I have seen in a particular strip, for all strip I have to calculate the work done and I have to sum it. If I do this summation, then it will become integration from A to B, capital F dot U unit vector will go, delta R will become dr, and U unit vector will go inside the dr, and it will become R vector. So the work done from point A to point B along a semicircle, along any path, is A to B, capital F dot dr vector. Since capital F is getting multiplied with this line, this is called line integral. Okay, so this is something that we refreshed whatever we had talked. Now we are in discussion for the kernel, the actual meat. I mean, nowadays talking about meat is like a crime. So actual, the fruit. So that we will talk now. So now consider this is x-axis, and we are considering line integral from point A to B and B to A. I am trying to calculate line integral from point A to A itself. So A to A line integral, any integral from A to A will be 0. But this is not the case here. We are trying A to B and B to A. That is A to A. We have talked it. If it is a straight line, if I have a vector field, and if I calculate A to B line integral plus B to A line integral, then it will be, certainly it will be 0. Is it the same case if I take more hops? I have taken one hop, A to B, B to A. Let's take more hop. So A to C, C to D, D to B, and B to A. So this would be a rectangle. So A to C, C to D, D to B, and B to A. Okay, so A to A line integral is nothing but A to C line integral, C to D line integral, D to B line integral, and B to A line integral. If this is 0, if this is 0, because I have taken a rectangle, then it is the line, then it is line integral is 0. Is it same that if I take A to A, I took a straight line path, next I took rectangular path. If I take any path, uh, circular path, if I take, so if I take circular path, then from A it make a round, came back to A. If I take parabolic path, any path, if I take a staircase, goes up and come down and then come back to A, if line integral is 0 for all possible paths, then it is called path independent. Path independent in the sense that whatever line integral we are calculating, that line integral will be dependent only upon the beginning point and end point. That's why it is 0. Because if I say A to B, B to C, C to D, A to C, C to D, D to B, B to A, what is the line integral? Anyone would say, actually you have broken the integration. Actually it is A to A and it should be 0. But sometimes it does not happen. If it does not happen, then it is called not path independent. If it is path independent, then it should be 0. Path independent means, path independent means that what, so line integral from A to A irrespective of any path I am taking. If it is 0, then it is in a closed loop. Then it is called path independent. Path independent if it is there, because we have taken so many paths, this proves that if I calculate work done from point A to B, work done from point A to point B, this work done is, since it is path independent, I have taken so many paths from A to A, then result is same. This proves that this integration is not dependent upon the path. Makes sense, right? If I have taken A to C, C to D, D to B, B to A, so this is the path I have taken. Now if it is circular, then there will be another path. If I had taken a straight line, then it was A to B, B to A. If it is circular, then I'll take an A to C, C to D, D to E, E to F, F to G, H, H, B, B to A. I have taken circular path and many hops. Whatever I do, if begin point and end point, it depends upon begin and end point. Result depends upon begin and end point, because begin is A, end is A. I have taken so many intermediary paths points and along so many paths, but at the end result matters only begin point and end point. If begin point and end point is A to A, means this line integral is 0. This proves that it does not depend upon the path. It depends upon the begin point and end point only. So if I say, I have taken circular path, then capital vector F is same in all calculations. R vector is changing. R vector, first it was straight line, then rectangular, then circular, whatever it is. So R vector I keep changing, but at the end result is A to A, begin point and end point. If begin point and end point, the result matters only on begin point and end point, this integral, then we'll call it, certainly this integration is not dependent upon the path or intermediary point whatever we are taking. At the end, what is the conclusion? Conclusion is, from begin point and end point, I took so many possible paths, but integration result is same. Means this vector field or force field is not dependent upon the path I take. It is dependent only upon begin point and end point. So if I take begin point A and if I take end point B, and if I connect through a straight line or through semicircle or through paraboloid, whatever it is, if the line integral is same, then or possible path, then we call the force field, vector field, as line independent. If it is line independent, then result only matters on the force field, whatever the integration we are getting. Certainly it will depend upon the force field, because force field has magnitude, right? So the end result will have dependent upon the force field and begin point and end point. So if capital F dot dr vector integration A to B, then it results in a algebraic function small f, then end result is small f b function over b, small f bracket open b bracket close minus fb, small f fb minus fa. So whatever integration we are doing, if this result is constant, that is fb minus fa, irrespective of dr vector, then this is path independent. We have seen that if it is path independent, then vector field capital F must be, if I have a potential function of small f, that is the result of line integration, small fb minus fa is the end result, then small f is the result what we are getting, that only depends upon the a and b, the end result fb minus fa. Capital F dot dr vector integration a to b equal to small fb minus small fa function, algebraic function at point b minus algebraic function at point a. If that is the case and it is path independent, means if I keep changing r vector does not matter. Only vector field capital F and limit a to b matter. If that is the case, the end result what we are seeing, fb minus fa small f, it is only dependent upon capital F a to b. A to b anyway we have. This proves that the small f is only dependent upon capital vector field vector field capital F, not on the R vector. A and B, anyway A and B is there. Small f, fb minus fa is the end result. It has three entities. But in integration has four entities. A to B, capital F vector dot dr vector. It has four entities. But at the end result is fb minus fa. If it is path independent, then it will always be fb minus fa, whatever r vector you take. This is what we saw. B and A is anyway there. Then this proves that small f, that is a potential function, algebraic function, that is the result, that is only dependent upon the vector field capital F. This is what we saw. Then it is path independent. This proves that there is some relationship, direct relationship. What is that relationship? Is capital vector field F equal to gradient vector of algebraic function small f. So small f is an algebraic function for which the gradient vector is capital vector F, then it is called path independent, because we have seen that if it is path independent, then actual calculus is A to B integration gradient of a small f dot dr vector equal to small fb minus fa. This is actual calculus for the path independent. If this is path independent formula, A to B integration gradient of small f dot dr vector, that is equal to fb minus fa small f, then gradient of f has to be vector field capital F. So capital F vector field, if it is gradient of any algebraic equation, potential function small f, if this is the case, then it is path independent. We saw it. If vector field capital F is x plus yi plus 0j, then there is no potential function exists, algebraic equation exists, for which if I calculate gradient vector, then it will be x plus yi, not possible. So x plus yi vector field is path path dependent. But xi plus yj, but xi plus yj, if this is the vector field, xi plus yj, if this is the vector field, then this is path independent. It is path independent because there is a potential function x square by 2 plus y square by 2, for which the vector, if I calculate the gradient, it will be xi plus yj. So for xi plus yj vector field, certainly one algebraic equation x square by 2 plus y square by 2, that is small fxy, exists, for which gradient vector is xi plus yj exists. This proves that vector field xi plus yj is path independent. Anyway, we will not talk more on it. We talked this so many times. Now consider that I have a vector field that is x plus yi, x plus yi, in bracket x plus y, outside the bracket I. This is the vector field plus 0 j. There is no component along jx. That is the vector field. So vector field is in along the x-axis. Now consider I have a point A, C, D and B, then back A. What is the line integral along a rectangular path? If this is the side and vector field is along x-axis, this is y, then it will be perpendicular to this. Then work done or the line integration along this line is 0. Similarly, along this line is 0. What is the work done from C to D? What is the vector field? Vector field equation is x plus y I. Consider this y is 10, then it is x plus 10 I. So x plus 10 I is the vector field, and then line integral, whatever the distance, that is C and C to D, whatever the distance is, that is the distance. So that distance multiplied by x plus 10. So that is the work done. So A to C, C to D, D to B, B to A. A to C in line integral is 0 because I have vector x plus y I. So I vector and y direction is 0. C to D, the integral is from C to D integration of I plus 10, because y I have taken 10, I plus 10 dot dr dot dr. So r dr vector, r is nothing but I vector. So dr is dx, dr is dx. So x plus 10 dx from C to D. That is the work done. Now this side 0. The B to A is xi because y is 0. So xi, and then so C to D work done is x plus 10 dx from C to D, and here work done is x dx from B to A. B to A, the length is same as C to D. It is a rectangle. This proves that it is non-zero. It is non-zero. Point A to point C work done is 0. Point C to D work done is integration from A to C to D, x plus 10 dx, work done is 0, and B to A integration x dx from B to A. B to A will be work done will be negative. It is opposite to the force. C to D work done will be positive, but that positive is higher than B to A. So net line integral from A to back to A is not 0. If it is not 0, can you think something about it? If it is not 0, will it produce a torque? Torque. Okay. So if I have a rectangle, consider this is rectangle. Okay. How I can say? Okay. It is rectangle. Consider this is a rectangle. If this is a rectangle, then this portion of the rectangle, here the work done is more, means force is more. Here force is less. Then if there is a water flow in a river, if there is a flow of water and if person is entering into the river, okay, consider this is a river. This is actually a river. This is xy plane, and there is a river flowing. River is flowing from left side to right side, minus x-axis to plus x-axis. So the vector field is x plus y I. Now a person is entering river from here, but the force of the river, this side force is more, this side force is less. The person is entering into the river. The force when he is entering at that position, force is less. Force should be same. But as he goes along, force is increasing. So the person, if a person or any body, any entity, if it is flowing in a river, then top side it will get more torque and bottom side it will get less torque. Then it will rotate. That's why there is a whirlpool that is typically get formed in a river. Why it whirlpool is not permanent? Sometimes you see suddenly whirlpool forms and then it disappears. At that moment, there is change in the force field that somehow it happens. So if river is flowing and if I am going from x-axis towards y-axis, then there is a force field is there. Then dfy dy, as we change the y-axis along y-axis, if there is change in the force field that is seen, dfy by dy, or rather if I say the force field is along x-axis, then f1, the capital F, that is the vector field or force field, it has two components, F1, F2, F1i plus F2j. Its components along x-axis, its component along y-axis. There are two components. If they come together, it makes a vector field or force field that is capital F vector, that is F1i plus F2j. If this is F1 that is going in x-axis and F1 is here, it has different magnitude, and F1 what is here along, this is x-axis and this is y-axis. River is actually flowing like this. Okay, I have rotated like this. This is x-axis and this is y-axis. Now the force field that is along x-axis f1I, it has magnitude here, some magnitude. If it goes along y-axis, then magnitude is changing because it is x plus yi. If that is the case, then what is df1 by dy? If this is f1, it is going left to right, how much f1 is changing if I change along y direction? If I make unit change along y direction, then how much f1 is changing? df1 by dy. If df1 by dy is very high, then force vector magnitude, the power of the force, it is less here, suddenly it is start increasing heavily. If any person is going in a river, top side, he is getting top class force. Bottom side, he is getting less force, but both force are in same direction. If someone sees that river is flowing in one direction only, then person if he goes, then suddenly he will be flown away. It will be flown away, whatever along the river. Not true. If river force, if river is flowing from minus x-axis to plus axis, then what is the force that we are seeing in the river? That is f1I. That is the only force. f2I is not, f2j is not there. Consider if that force is growing, here force is different at the if it goes along and deep in the river, force is different, then there is certainly per unit change of y, there is change in the force magnitude. df1 by dy is there. If df1 by dy is very less, then more or less person will be flown as per the river. So river will do work done to flow the person along the river flow. But if df1 by dy, that change in height, then he will start getting torque. It is as good as someone is pulling that person on top this side and someone is pulling on this side, because there is a difference. Though both are pulling in same direction, and person will move from left to right true, but he will start rotating. This is curling. Curl means what is the curl factor of a vector field F? Curl factor means tendency of vector field F to rotate something. Okay. Now I'm not talking about the river. Let's talk about any vector field which has equation as can. Let's talk about this is the vector field. This is the vector field, that is x plus y I. Consider a vector field that is x plus y I plus x plus 2yj. Makes sense, right? X plus yi plus x plus 2yj, that is the vector field. So vector field will not be only along x-axis, it will be something like this because it has x component and y component. Now I have point A to B, point A to C, rectangle. There is a rectangle now. Point A to C, C to D, D to B, B to A. So what is the line integral from A to A? That is A to C, C to D, D to B, B to A. Then line integral from here to here, here to here, here to here, here to here back. That is A to A. A to A will be 0. No, because I have calculated it is x plus yi and it is not 0. Not true. Because I have introduced yj component in the vector field. Now it is x plus yi plus x plus 2yj. If that is the case, then will the line integral will be 0. Now this side is playing role because there is a vector field. When vector field f2 component has arrived, that is x plus 2y. If that is the f2 component that is along j axis, then this is receiving work done. This is receiving the force. Earlier force was in this direction, so no work done in this direction. So work done magnitude was 0. This side and this side also. No work done is there. Now earlier x plus yi plus 0j, work done was along this direction and this direction. And this direction work done was more, so it was getting a curl. Now work done it is in this direction also and this direction also. What about if this work done in this direction, work done is less, work done is more, and in this direction, work done is less. Okay, if this direction, now I'm calculating work done along this direction, then work done along this direction, work done along this direction. Okay, consider this work done along this direction is negative. Negative means work done is happening is this direction, and it is more than the work done that is happening in this side. Consider the work done along our vector field is like this, right? If vector field is like this, then it has positive y component. It has positive y component. If that is the case, then work done from here to here, force it is receiving force in the direction of displacement. If this is the displacement, then y force is in same direction. But if consider this, then work done from here to here, but force is here. So work done is negative. Work done is actually in this direction. Then this and this, if I calculate, and this work done is more, that is in this direction, then it is giving opposite curl. If this is rectangle, one side, another side, and this side work done is in this direction. Sorry, force is in this direction, and we are calculating work done from here to here. Okay, and here in this side, force it is in this direction, we are calculating work done from here to here. What we calculated, this work done is more. But anyway, okay, if I calculate b to a, then work done is negative, means work done is in this direction. Makes sense, right? If this is rectangle and work done from C to D is along this direction, D to B and B to A is negative, means work done is in this direction. But this direction work done is more. Now if I calculate work done from A to C and force is in this direction and displacement is in this direction, then work done is in this direction only. Okay. Now this and this. Now displacement is in this direction. Displacement is in this direction. Force it is in this direction. So work done will be negative. I am calculating work done this side, but it's in negative. Work done is in this direction. If this direction work done, and here also work done is in this direction, the work done is along the force direction only. If work done is in this direction, work done in this direction, if this direction work done is more, then net work done along this direction is not zero. It has some amount, and net work done from this side to this side work done is more. If these two side work done, if they negate each other, then net curl in the line integral is again zero. Again zero. Can you see this? So the line integral, if point A to A, that is closed loop line integral, if df1 by dx is there, df1 by dx is positive, then there will be curl, but not necessary. If df2 by dx, this is f2, right? If there is a vector field, it has f1 and f2. If there is f2 and df2 by dx is there, f2 at this point, A to C is different, and D to B, that f2 is different. If f2 is different, then f2 by dx is there. If df1 by dy and df2 by dx, if there is some relationship, then curl can back be 0. If that is the case, then line integral will be 0 and it will be path independent. Unbelievable. This proves that if person is swirling, turning around in the river, he can be saved. If I blow some wind that has df2 by dx, if water has, or there is a boat, I think that is a better example. If boat is crossing the river and suddenly it starts rotating, then can I save the boat? Yes, you can save the boat. If you blow a wind that has y direction. If river is flowing in x direction, that is f1 component. If you blow a wind, that is f2 component, and df1 by dy and df2 by dx, if there is some relationship and if I maintain that relationship, then net curling will be zero. Both can be saved. Okay, so we will land up into Green's theorem. Now we are landing up into Green's theorem, where we can have curling, not curling. What is the actual situation? That is df1 by dy, df2 by dx. If f1 component of vector field is changing as we are changing the y, and f2 component of the vector field is changing if we are changing the x component in the next component of vector field f2. If that is the case, then curl can still be zero, means line integral will be zero for all possible paths from a to a, and it can be path independent again. Okay, so this is Green's theorem that we will